Okay, elastic potential energy. So I would like to talk about elastic potential energy in general, and then I'd like to specifically show you how to solve the problems in your homework. And sorry if this is jumping around. I'm still not entirely used to making these videos directly onto the computer. I prefer my paper, but I'll stop being such a Luddite and just get on with it here. So elastic potential energy, what makes this kind of energy different from the ones you've studied before is it is the result of a force that is not constant. You know, energy is the ability to do work. And this, here we go. Energy is the ability to do work. And work is force multiplied by distance times the cosine of the angle in between them, because it's the degree to which, or the extent, I should say, to which the force is in the same direction as the distance. And this is all well and good if you have, say, a block, and you exert some applied force F at A over some distance D. Then the work that you've done to the block is quite simply equal to, sorry, there we go. I was just trying to move that. Okay, so you have a block and you want to apply a force FA and move it a distance D. Then the work that you've done is equal to that force multiplied by the distance. And you've learned that that gives it a certain amount of kinetic energy. So the kinetic energy that you've given the block is going to be equal to F times D. Now, that doesn't really work when we talk about how much work it takes to compress a spring. So let's say you have a spring here and you compress it a distance X. So we're compressing the spring to there. So it started out at this distance here, and we've shrunken it by applying some force this way to compress it a distance X. The reason why we can't simply say that the work is equal to the force times the distance is that force is not constant. If you have a spring, it takes a tiny little force to compress it a little bit, but it takes a much greater force to compress it a lot. You know that from pushing on a spring or pulling an elastic. In ideal conditions, it follows this rule here where the force is equal to some constant, which is specific to how stiff the spring is, multiplied by the distance, how far you've compressed it. The reason why there's a negative there is the spring, this is the force the spring exerts back on you, and it's in the opposite direction of the direction that you have pushed it. So if I push the spring this way, the spring exerts a force back on me that way. That's what that negative means in that formula. Anyway, as you compress a spring, you're not exerting a force, you're exerting a series of forces. It's like this little force to compress the spring a little bit, and then a greater force to compress the spring even more. And then the more that spring has been compressed, the greater and greater the force you must exert on it. So instead of multiplying a single force by this distance, you have to actually multiply several different forces over the smaller distances that add up to give you that distance. So it's like this one, plus this one, plus this one, plus this one. But that's only an approximation because we would have actually an infinite number of these taking infinitely small steps. But then the closer we get to fully compressing the spring, the greater the force is. What that looks like when we plot it mathematically is simply a line. If you're compressing a spring, the force that you exert to compress the spring a distance x it depends on this line, Kx, where K is the stiffness of the spring. So if a spring is stiffer, then it would take a steeper line. And if the spring is less stiff, then it would take a shallower line. Okay. So how much work does it take to compress the spring by a distance x? Well, the idea here is you add these rectangles up. They're the products of the little force times the little distance, the next little force times the next little distance, and so on. So what that amounts to is the area under here. So the area under that curve is equal to the work that it takes to compress a spring. So if I have a spring, whoops. So if I have a spring and I want to compress it a distance x, the amount of work is going to be equal to the area under this curve. Well, this line, I should say, where the line is defined by the graph kx. So the area is half base times height. Now, what is my height? My height is the force that I have to exert on that spring, but it actually turns out to be proportional to how far I've compressed the spring. So that gives us half of the base times the height is kx. So that gives us this equation, half kx squared. And that is how you determine how much work it takes to compress a spring. And it's also equal to how much potential energy is in a compressed spring. The amount of energy in a compressed spring is proportional to the spring constant K and the square of the distance it's been compressed. So let me do like a clear numerical example. So let's say I have a spring and the K value is 10 newtons per meter, and I compress it a distance of half a meter. So what have I done? I've taken this spring and I've compressed it by half a meter. The amount of work that it took me to do that and the amount of energy that is now stored in there is equal to half kx squared, or half of my 10 Newton meter spring, that's the stiffness of my spring, times x, which is 1/2 squared. And when you square a half, you get 0.25. So that ends up being 0.25 times 10 is 25 divided by 2. So it's 12.5 joules. So you've got 12.5 joules of potential energy. Let me just run that through my calculator and make sure. So I've got a half of 10 times 0.25. Yeah, got the decimal off by a spot. It's 1.25, sorry. Yeah, I'm sure you got that right as you follow along here. So that's 1.25 joules of energy that it takes to compress a spring of K value 10, a distance of half a meter. Okay, so let's answer some of these questions here. Let me find them. Okay, here we go. So we've got a spring with a K value of 100 newtons per meter is compressed by 15 centimeters. How much work was done to the spring, and how much elastic energy does it store? They're the same amount for each. And so this is just simply 1/2 kx squared. So your K value is 100, so half of that is 50, times your X value is 0.15, and we're going to square it. And that should give you 1.125 joules. So that first one there should give you 1.125 joules using half kx squared. Second question here, You've got a 1.2 kilogram block sliding on a frictionless surface until it hits a spring and compresses it. If the spring constant is 150 newtons per meter, how far does the spring compress before it stops the block? So what are we doing here? We've got a block, and our block is sliding along, so it has kinetic energy equal to half mv squared. And m is 1.2, and v is, I'm assuming it was given, v is not given, so this is not really a good question. Let's say that 1.2 kilogram block is sliding on a frictionless surface at 1 meter per second. Okay, so we've got our 1.2 kilogram block, and it's sliding along at 1 meter per second. So how much energy is in that? I've got 1/2 mv squared. So that's 1/2 of 1.2 times 1 squared. So that's going to be 0.6 joules of energy. So I've got 0.6 joules of energy in that block that's sliding along until that block collides with a spring. So the block is moving along and it hits a spring and it compresses the spring. So the spring is going to push back on the block until it stops, so until that velocity arrow disappears. And the question is, how far has it compressed the spring? And we're going to solve this problem using energy. The kinetic energy lost is going to be equal to the elastic energy gained. So the change in kinetic energy is going to be equal to the change in elastic energy. And how much kinetic energy did we lose? We lost half mv squared. And how much elastic energy did we gain? We gained 1/2 kx squared. Now, x is the only unknown in here. So you've got 1/2 of 1.2 times 1 squared is equal to 1/2 of, and I believe I made this spring 150. 150 newtons per meter. So that's equal to 1/2 of 150 newtons per meter times x squared. So we can cancel out the halves. We can divide out the 150, and then we can square root both sides and we'll find x. So that makes x equal to the square root of 1.2 So I've got 1.2 multiplied by 1 divided by 150, and we're going to take its square root, and that gives us 0.089. 0.089 seems small, but actually not so much. That's in meters. So the 0.89 actually means 8.9 centimeters. So the spring has been compressed 8.9 centimeters while the block was stopped. General strategy with these is the block's moving along, and that moving block has a certain amount of kinetic energy associated with it. And that kinetic energy got turned into spring energy or elastic energy inside that compressed spring. And we set up our equation so that the amount of kinetic energy lost is equal to the amount of spring energy gained. And then if we're just down to a single variable, we can solve this problem. Okay, so let's look at another problem here. All right, let's consider a case where the block is dropped onto a spring. So let's take, we take that 150 Newton meter spring, we mount it vertically, and we drop the 1.2 kilogram block on it. We place it on it. How far down will it eventually rest? So in this question, we've now got a 150 spring, (150 newtons per meter), and we're going to place a 1.2 kilogram block on it, and that block is going to compress the spring. And the question is, how far is it going to compress that spring? So I'm going to call that X. So what happens? As the block lowers, we lose gravitational potential energy. So we have a change in gravitational potential energy, and that's going to be equal to our gain in elastic energy. And our change in gravitational potential energy is going to be equal to mgh, and our change in elastic energy is 1/2 kx squared. Now, we know that k is 150, we know that g is 9.8, assuming we're on the Earth and near the surface, and we know that m is 1.2. So that kind of leaves us with two variables here, which is a little bit of a problem. So you've got 1.2 times 9.8 times h, and that's equal to 1/2 of 150 times x squared. So you can't really solve one equation with two unknowns. However, have a look at this picture. How far did the block fall? It fell exactly the same distance that the spring was compressed. So that means h and x are the same thing. So knowing that h is equal to x, because the distance the block dropped in this case is equal to the distance the spring compressed, we can now say that 1.2 times 9.8x is equal to 1/2 of 150 times x squared. So we can divide both sides by x and then do a little bit more, we call that arithmetic or algebra to this, not quite sure what to call that. We'll multiply both sides by the 2, so we've got 2 times 1.2 times 9.8, and then we're going to divide that by 150. We've already dealt with the fact that x was squared by canceling one of the x's. See, that was x times x with that x over there. So all of that is going to give us x, which is the distance the spring has been compressed, and it's also the distance the block has fallen. And so that's going to be 2 times 1.2 times 9.8, and then we'll divide this by 150. And that gives us 15 centimeters, 0.1, or closer to 16, 0.157 meters, or 15.7 centimeters. Okay, how does this change if the block is, well, there's a couple of discussion questions, so let's answer those as well. So in the discussion question, if the spring is ideal, that is, no energy is lost as heat or sound when it's compressed, what will happen after the block is placed on it? And the answer is it'll oscillate, meaning if this is perfectly ideal, if no energy is lost, then when you drop the block on the spring, that block is going to compress the spring. So we'll be down here, and then it's going to bounce back up. And then through gravity, it'll compress it again. And it'll cycle like this. It'll actually follow a sine curve in its height. It'll cycle like that forever. I apologize. A cosine curve could start at the top. Got me. All right. That's if it was ideal. Realistically, that's not happening because that moving block is going to experience drag. That's air resistance slowing it down. And also, as you compress or as a spring stretches back out, it's going to heat up. So energy, mechanical energy is lost as it gets converted into the movement of the air and heat. And if it makes any noise at all, sound as well. So those are forms of energy that the motion goes into and then gets lost from the system. So what'll end up happening actually is it's gonna, instead of following a cosine, it's gonna follow a, we call that a damped harmonic oscillator, if you want to look that up. The mathematics behind it's kind of neat. It's in what we call an exponential envelope because the height decreases exponentially, and you can actually prove that quite easily. Well, we'll do so on a later video. Okay. So ideally, it's just going to oscillate, bounce up and down forever. Realistically, it's going to bounce lower and lower until it stops, and you know that. Okay, next is a bungee jumping question. I'm not going to put in these numbers and spoil your fun answering this question, but I'm just going to sort of help you set it up here. So instead of doing the bungee jumping question, I'll do one where the physics is the same. We have a spring, and we have a block, and we're dropping the block from a height onto the spring. So spring's got a value k, block's got a mass m, and it's starting out a height h, and that height h, or let's call it, we'll call it h, that's its height above the spring. Upon dropping it, you know that spring is going to compress, and the block is going to end up down here. However, stop and think for a second. Is this going to end up lower than in that previous case? There we go. Is this going to end up lower than in that previous case where we set the block on the spring? So we had, where was it now? Yeah, we had this case here where we gently set the block on the spring and it compressed a certain amount. Now, what if you were to lift that block up? And, what if instead of just setting the block on the spring, you were to now lift it up and drop it on the spring? You know it's going to compress that spring even more. Here's how we account for that. The loss in gravitational potential energy is still equal to the gain in elastic energy. So when we set this up, I used h for that height. Let me change that. Let me change that to an L. Let's say we're distance L, so that's like the length. We're a distance L above the spring. And then when that mass lands on that spring, it compresses it a distance x. So what is our change in gravitational energy? Our change in gravitational energy is mgh. Our change in elastic energy is half kx squared. Now, we've got to know some of these things to be able to solve this. So let's assume that we know m. We know the mass, we know we're on the Earth, so we know g is 9.8. We know something about the spring's stiffness, so we know the k value. So that gives us two unknowns, the height and x. And in the previous case where the block was just set upon the spring, they were identical. But in this case, they're different because the block is being dropped from above onto the spring. That's just like the bungee jumping question I gave you. See, in that bungee jumping question, you have a man who's up here, and there's his bungee cord, and he jumps, So he gets to a point where that bungee cord, he's fallen like the length of the bungee cord, and that's where it begins to stretch, and then he stretched that bungee cord down. And so the distance he has fallen is this much greater than the distance he has stretched the cord by, because he's falling with a slack cord for a while. So how do we set that up? Just take a very close look at this picture. You'll see it's actually not that bad. What is the height that our block has dropped? The height, the block has dropped from here to here, is L, the length, or that distance that it was above the spring. That's our L value, plus the distance the spring has been compressed, the X value. So when you go to set this up, you're going to say H is equal to L, that's like the length of the cord or the distance you are above the spring, plus X, the distance the spring has been compressed or the cord has been stretched. So then that's going to change into mgx plus L equals 1/2 kx squared. And your only unknown in this is going to be x, which you've now got a quadratic. When you expand that out, it's going to be a trinomial quadratic, so you might have to drag out the quadratic formula. However, I'm assuming that by the time you're studying this, you're quite proficient with that. And yeah, best of luck. And I hope you learned something from this. Sorry about the video jumping around as much as it did. Let me try and recap. So to recap what we've talked about here is we're talking about work is force times distance. However, when you do work to a spring, that force is not constant. So you can't just go force times distance because you don't have some constant force to multiply. So what we do instead is we look at the area under this curve. And the area under that curve gives us this formula, 1/2 kx squared. 1/2 kx squared, let me write this out again, memorize that. It looks just like half mv squared. 1/2 kx squared is the energy stored in a spring or an elastic, where k is the stiffness. So like a thicker, stiffer spring is going to have a larger k value. And x is the distance it's compressed or stretched from the rest position. I can't fit all that in here. So it's the movement of the spring, the compression. Let's call it the compression. Compression. That's the compression of the spring, compression or the stretch of the spring. It's how far it's moved. So let me just draw that out. So if the spring was there and the spring or elastic is now here, x is how far we've stretched or compressed it from its rest position. And if you square that and multiply it by k and divide it by 2, that tells you how much work it took to do that, and it tells you how much energy that it now has and is capable of releasing as the spring springs back or as the elastic snaps its way back. So we're able to solve problems using that. So we could solve problems like, if you have a moving block, how far will it compress the spring? You take the kinetic energy in the block, and all that kinetic energy gets turned into elastic energy in the compressed spring. If you set a block on a spring, you take the gravitational potential energy the block has, and it turns into elastic potential energy in the compressed spring. But if you were to drop the block from a height above it, still the gravitational potential energy lost is equal to the elastic energy the spring has gained. However, you're going to end up with a quadratic because h and x are not equal to each other, but they are close. They're just off by the fact that it falls a little while before it hits the spring, so you got to add that in to x to get h. So h is actually x plus L, where L is the length that the block has fallen or the bungee cord is stretched before it hits. When you solve this, you're going to end up with a quadratic. That quadratic is going to have two solutions. And both of those solutions are often valid. What they're going to give you is two different places where your velocity is zero. And the way you can physically interpret that in the case of the spring, so you drop a block on a spring, well, the two solutions you get, one of them is going to be where you've compressed it down here, and the other one is meaningless unless the block attaches to the spring. You see, if the block attaches to the spring, it'll bounce up, but then all of a sudden the spring will stop it, and it's going to be connected, and it's going to be up here. So let's say the spring has a rest position here. When you solve that quadratic, you're going to get two different x values from the rest position, one below, one above. The one above is going to tell you how high it'll bounce up to, assuming it clipped onto the spring, which stopped it from bouncing back to its original height, assuming no energy was lost. And then on the bungee cord problem, again, you're going to get two solutions, and that's going to have to do with there's two different lengths that bungee cord will be stretched to, because after you've fallen, you're going to be down here, and then you're going to bounce back up to a certain height. So where the cord is compressed, so you're like, you were there, and then you're going to bounce back up to there, and you're going to continue to oscillate. So you're going to bounce up and down between those heights. And when you solve that quadratic, it's going to give you the two heights. So if you're solving for, I don't know, the safety in this system here, then you're going to want to go with the lower one, I guess.